All right, let's talk about high school grades. The percentage of college freshmen whose average grade in high school was an A was about 19% in 1970. And then that percent has been growing by about 0.8% each year. Create a table of values to describe the association between years since 1970 and the percent of college freshmen who averaged A's while they were in high school. Okay, let's do it. So, it looks like we have a percent and we have years since 1970. So I'm going to go years since 1970. And over here, I'm going to go percent. Percent averaging, having an A average. Okay, so let's rock this. That's a 3.6 and above, by the way. In the year 1970, that would be 0 years since 1970, it was 19%. 1 year later, it went up by 0.8%, so 19.8. 2 years later, it went up again by 0.8%. What would that put it at? 20.6? Another year later, it went up again by 0.8% about, making this 21.4%. Another year passes and it goes up again by 0.8%. Let's see. That plus 8 is 22.2. So 21.4 plus 8 tenths, 22.2%. Okay, so we see what's happening here. And I need you to know that people aren't getting smarter. It's just that the grades that are being given, just more people are being given A. So it's like the quality of an A has gone down, and so more people are attaining it. Okay. Use the table to write an equation that describes this situation. Ooh, I remember. Here we go. This one has a pattern. It has a constant increase of 0.8. Okay. And it has an initial value. Okay. Initial. It starts at 19 and then we add however many, we add 0.8 however many times. Okay, so for fun, I am going to call this T and I'm going to call this for percent, P for percent. So use the table to write an equation. I'm on it. The percent starts at 19 and we add 0.8 T times to get the new percentage. Rewrite your equation using function notation because we know it's a function because it's linear. For every input, there's exactly one output, no more than one. So P of T. We know it's a function. It's a function of time. The percentage has been a function of time. Compute P of 30. Okay. That means that this is T. T equals 30. So we would say P equals 19 plus 0.8 times 30. 30 of those. Well, 3 of these is, so what is that, 24? 80% of 30, I believe that's 24. 19 plus 24, well, that's very similar to 44, except minus 1, so 30. 43? Okay. I almost wrote 33, but 43. and explain what it means in the context of this scenario. Well, first of all, if t equals 30, that's 30 years since 1970. That makes the year 2000. So, in 2000, about 43% of college freshmen, about 43% of college freshmen had a high school average of an A. Okay. Averaged an A in high school. That's a lot. That's a lot, considering it was 19%, 1970. Predict the percentage for the year 2013. Right. So then we're going to have to figure out our T. T is years since 1970. So, 2013. How far away? What's the difference between that and 1970? Well, I think that's 43 years. So T equals 43 years. And now we can put that into our equation and see that P will be, all right, I'm getting out my handy calculator so that I don't screw this up. 19 plus 80% of 43, got it, 53.4. Okay, predict the percentage in 2013. That is what the equation predicts. I wonder, we could probably look that up actually. Predict when the percentage of college freshmen with an A average from high school will be 50.2. Well, now we're given the P. We're given the percentage. So, and we're not given the T, the time. So, it looks like we are taking our equation that we created from this situation. We could do this until we reach 50.2. That would take a while, so no. And so now we're using the benefits of what we learned from this section. So I put in 50.2 where the P was because that's the percentage instead of the time. And now I'm going to solve this. You could use your calculator and find the intersection point. I'm actually going to use algebra just because it's faster for me. But by all means, if you want to use a calculator, have at it. 50.2 take away 19 is 31.2. Okay, so 19 plus 31.2 is 50.2. And now I'm going to scale down by 8/10. So divide both sides by 0.8, and I get 39. But that doesn't make any sense. T equals 39? No. 39 years since 1970. Well, 30 years after it was 2000, so this would be in about 2009. That's when it happened. That is not a complete sentence, but I just don't want to finish the sentence. What is the slope of this line? Ooh la la. So now it gets a little bit more interesting. Remember, slope is this constant change, this constant rate of change, or the ratio of change. It goes up by 0.8% each year. Growing by 0.8% each year. And that is our slope. So what is the slope of this line? It's 0.8. What does it mean in the context? I prefer actually even labeling this. 0.8% each year. So the percent of college freshmen with high school A averages goes up by 0.8% each year. Okay, what is the p-intercept? Oh boy, now I have to go back and think. Okay, I'm going to rewrite this. What was it? It looked like, so y equals the response variable. I would prefer it with response, actually. Boop. The response variable is equal to the initial plus the constant rate of change times the explanatory variable. And when we rewrote this in m, x's, and b's, this was a b. Constant rate of change was in slope, the m, and the explanatory was x. Okay, so the b-intercept, or the y-intercept, is this initial value. And in this case, it's not a y, it's a p. So what is the p-intercept? 19. And what does it mean? Well, that's what it was in 1970. So the p-intercept is 19%. What does it mean in the context of this situation? The percentage was 19% before the constant increase after 1970. Okay, so that's what it was initially before it started doing this increasing business. Okay, special types of equations. Here we go. While commuting to work and running errands, a person travels 576 miles in a 3-week time frame. Estimate the time it takes this person to travel 1,000 miles commuting to work and running errands. Okay, here we go. So here's what I see. We have a ratio. We have a ratio of 576 miles in a 3-week time span. And this is asking for 1,000 miles and however many. Okay, so my students, they're so clever. So I've had students solve this in many different ways, but I feel like the one way that has always stuck with me was this. I had a student who took this and actually scaled it down per week. So they said, well, if 576 miles happens in 1 week, then this is equivalent to 192 miles in 1 week. Okay. But that didn't get us closer to how long it takes to drive 1,000 miles. And so then I was like, why do we need to know that? And then they said, well, if we're going to do that, then really what we could do, instead of scaling everything down by 3, which was nice, we could have made this a unit ratio in the other way around. Okay, so I was like, what? Okay. If it takes 1 week to travel 192 miles. Okay. Then we could scale both of these down by 192. 192th of a week for 1 mile. So they scaled this down to make it a unit ratio in terms of 1 mile, and then they scaled this up by 1,000. I was like, dang. And this really, I mean, it just really has stuck with me because I really thought this was kind of fabulous. So, scale them both down to get what portion of the week you had, and then scale them both up by 1,000. Right? So scale this up by 1,000, and if you multiply this by 1,000, and I can just actually write that. Right? So when they were doing this problem, they said, well, first scale it down by 3, then scale it down by 192, then scale it up by 1,000. And I was like, what? How did you make all of those decisions? And ultimately, they ended up walking me through this process, okay, that you're seeing before you. Now, 1,000 times 192nd is approximately 5.2. So that is, by the way, 5.2 weeks for 1,000 miles. And we usually don't say 0.2. 0.2 of the 7 days is like a day, just under a day and a half. So like 5 weeks plus 1.5 days about to take this person to travel 1,000 miles. Now, in your book and maybe in your past, like when the student did this, I was like, I love that. I couldn't have asked for more. Like, this is pure knowledge. And so I want you to know that if you looked at this problem, and replace the question mark with an X, you do end up with a proportion. Okay? And so if you go about this, and you could find a scalar from 576 to 1,000. I mean, just under 2 or something. But I have a feeling that a lot of textbooks tell you to scale up by 3, scale it by X, and end up with some type of equation like this. And then scale it down by 560. Okay? I want you to know you will get the right answer, but that you don't have to be pigeonholed into this procedure where you scale up by 3 and scale up by X and then scale down by 576 in that order. So what I mean by that is the student in my class, first they simplified it, then they scaled down by 192, and then they scaled up by 1,000, and that worked swimmingly. Okay, so I need you to know you don't have to just be pigeonholed into one way to solve a proportion. And as a matter of fact, this way of solving a proportion usually confuses people, and they end up making mistakes because they're like, why does this work, or how does this work? And the reality is, if you're okay with ratios, then you should be able to get through this problem even without it. So just so you know, it took us a few more steps, but nonetheless. So I wanted you to see it book way, and I also wanted you to see it former student way. What assumptions did you make while solving the previous problem? Ooh, now that is a really good question. Because in order for this to be true, we have to assume that they commute to work and they run the errands about the same amount or at a consistent rate every week. We're really kind of banking on the fact that their weeks are pretty much the same. So the assumption that we made was that all of this is an equivalent ratio, an equivalent rate, a proportional rate, and that means we assumed is consistently the same. Or constant if you want to say constant. All right. In a poll of 2,209 adults, 1,679 of them said professional baseball players who use steroids should be banned from the National Baseball Hall of Fame. Estimate how many of the 16,000 students at ECC would say players who use steroids should be banned if we use this to make our inferences. So if we use this sample to make our inference, how many ECC students would that be? All right, here we go. So let's go like this. 1,679 banners out of 2,209 adults, okay? And we need to scale this up. So is equivalent to how many out of 16,000? And I'm going to say it. I'm going to tag you as an adult. So please start adulting. Okay, 16,000 adults. Yeah? Okay, so if we go ahead and make the leap and equate that students at ECC are now adults, then again, we are just scaling this. We are using ratios and proportions. What would be easiest? I feel like the easiest thing to do would be actually scale this down by 2,209 adults and then scale it up by 16,000. So here we go. Or essentially we're creating a percentage, by the way. So okay, scaling it down. Scaling it down by 2,209, and then I am going to scale it up. Let's see. So okay, so just so that you see what I'm doing, right? Scale it down by 2,209 adults, and then scale it up by 16,000 adults that are ECC students. And let's see what we end up with here. So 16,000 times 1,679 divided by 2,209. And we get approximately 12,161 ECC students, aka adults. Okay, so I need you to know something. Again, the book would have solved this differently. They would have just taken this, put an x here, and multiplied both sides by 1,600. Because x divided by 16,000. X divided by 16,000, to undo that, multiply by 16,000. But I want you to see that's the same thing we did here. So you could use a proportion, and or you could use ratios, equivalent ratios, because remember that equivalent ratios are proportions. So however you want to view that. But this answer does make sense. I'm looking back to see if that does make sense, and sure enough, it does. Okay, quick remark. Every math model makes assumptions. So we just made a huge inference, like a leap from whoever they had sampled to specifically ECC students as well. But every math model makes assumptions, okay? It is best to disclose them. If you want to be trusted, you got to just be really forthcoming with all of your assumptions. So up here we talked about if this is going to actually work out, we had to make this assumption of it consistently being the same. And in this situation with the sample of adults, we have to make an assumption that their sampling will still represent our population of ECC students. Okay, I don't know. Who knows, right? Like, it could. I don't know which way it would go in terms of like older adults versus traditional ECC students. What is the average age? Like 24, 22, I forget. Anyway, so like maybe there's an age gap that I don't know, but it just says adults. So should include all of them, including young. All right, so just to make a brief summary here, right? In section 3.3, you solved linear equations. We also solved some proportions, and we described what these solutions mean in the context. While we were at it, we went ahead and remembered that if we are going to look at linear equations and solving them, then don't forget that these are lines and that we know some properties about lines. Like we know their pattern and we know their picture, and so we can use those together to talk about, okay, we have a linear equation and it looks like a line, and we can, exploit and use our graphing calculator to kind of work with that. In addition, let's not forget that we know many things about ratios, and we've actually been doing a lot of conversions in this class. And at the end of the day, proportions, while we can say that they are linear equations or sometimes a form of linear equation, not here, but here, yes, that still is just a matter of converting or using our knowledge of ratios or constant rates of change. Okay? So let's not forget, while we solve linear equations, that yes, we have algebraic skills, but we also know some things about lines.